back to the last leg of module 3 on finite difference method. We are working on the applications of finite difference method to scalar transport and its computer applications. Now let us have a recap of previous lecture, the lecture 8th which we had earlier. We completed self-centered grid development for finite difference discretization for 1D heat conduction, and we also discussed how this simple approach can be easily extended for multi-dimensional problems. Then we discussed application of finite difference method to 2-dimensional heat conduction, transient heat conduction, and today we are going to focus on, in today's lecture, on advection-diffusion problem and computer implementation aspects. So a brief outline of what we will do today: application of finite difference method to 1-dimensional advection-diffusion problem. Extension to multi-dimensions would be fairly simple. We will have a brief look at different schemes which are available, different difference schemes for advection theorems, and we will then focus on the computer implementation of the algorithms which we learned so far for real life CFD. Primarily we will have a look at the choice of languages which are used, programming paradigm, and data structures. Now let us first take 1-dimensional advection-diffusion case. So if we are dealing with a steady state problem, 1-dimensional advection-diffusion for a scalar variable phi is governed by d by dx of rho u phi. This left hand side, this term we would call as convection term, because this represents the advection or convection of a scalar phi due to velocity u. On the right hand side we have got d by dx within bracket gamma d phi by dx, where we presume that gamma may be a function of spatial variables. So this term we refer to as diffusive term. Now this usual symbols, u stands for specified velocity, rho is density. In what follows we are going to assume that maybe these might be considered as constant, and gamma is diffusivity. Now let us take a typical boundary value problem. Suppose phi values are specified at both ends of the domain of length L, then boundary conditions are phi at x is equal to 0 is equal to phi naught, where phi naught is specified value, and similarly at the right end phi at x is equal to L is phi subscript L. This phi 0 and phi L, they would both denote the specified values. Incorporation of gradient boundary conditions would be exactly done in the same way as we have discussed earlier for 1-dimensional conduction problem. Now let us see our choice of schemes which we can have. We will primarily choose central difference scheme for finite difference approximation of diffusive term, that is the second order derivative which we had in the right hand side. For convective terms on the left hand side we can use CDS, that is central difference scheme, or Upwind scheme. And once we have done our discretization, a discretized equation for an interior node I can be represented in our standard template form, that AP superscript I, that coefficient I for current point P or ith node, phi p plus AWI phi I minus 1 plus, instead of phi this would be capital I and this would be small phi at I plus 1 is equal to Qi. Now let us note that these coefficients which have put AP, AW and AE, they contain the contributions coming from the finite difference discretization of both convective and diffusive terms. That is to say, we can break it into two parts, A is equal to A superscript D plus AC, and we will have a look at how do we get these components with different choices of our discretization scheme. Now let us first have a look at the contribution which comes from the diffusive term. We have represented our discrete equation at node I as an interior node I. Let us draw a standard grid. This is our left end, x is equal to 0, and this is x is equal to L, and if we use our vertex centered finite difference scheme, these nodes would be numbered 1, 2 and so on. So, ith node I minus 1, I plus 1, and the last node would be numbered as n plus 1 if we had n number of divisions. So, we wrote our generic discrete equation at node I as A P. The subscript P stands for our grid node I, and to reinforce this put a superscript I as well. So, API phi I plus AW I, W stands for the I minus 1th grid, plus AE I phi of I plus 1 is equal to QI, and we said any of these components at A's, they will consist of two parts, one which is contributed by the diffusive term and another one which is contributed by the finite difference discretization of convective term. So, now let us first take the case of diffusive term, and how do we discretize it? We have already seen its discretization in detail, so we will just put a summary here. We would use central differencing. So, what we are looking at? We are looking at a term del by del x of gamma times del phi by del x at node I, and we said, look, this we would discretize using the central difference formula. So, we are focusing on our grid node I. So, let us choose these two intermediate node points I plus half and I minus half. So, in terms of these values, the outer derivative can be approximated as gamma times del phi by del x at I plus half minus gamma times del phi by del x at I minus half divided by x of I plus half minus x I minus half. Now, the derivatives which appear in the numerator, we would again use series. So, series for first order derivatives in a numerator. So, that will give us gamma del phi by del x I plus half. This can be approximated in terms of the values at node point I plus 1 and I, because I plus half is the midpoint of I and I plus half. Gamma I plus half phi of I plus 1 minus phi I, and let me revert back to delta notation. So, delta xi similarly del phi by del x I minus half. This can be approximated as gamma I minus half phi of I minus phi of I minus 1 divided by delta x I minus 1. Okay. So we can substitute the expressions for these expanded variables or the expansions for the derivatives appearing in numerator, and thereby we can obtain the final form for the diffusive term del phi by del x gamma times del phi by del x of I gamma I plus half phi of I plus 1 minus phi I delta x I minus 1 minus gamma I minus half phi I minus phi of I minus 1 delta x I, this whole thing divided by 1 by 2. This x I plus half and x I minus half, their difference can be represented in terms of delta x I and delta x I plus halves, or rather we can simply write it as 1 by 2 x I plus 1 minus x I minus 1 delta x I delta of x I minus 1. You can simplify this expression further, and that I would leave as an exercise to simplify this expression. That is, all that you need to do is collect terms in phi with same subscript together and obtain expressions for API, APD, AWD and AE of D. So, this I would leave as an exercise for you. It is a fairly simple exercise. So, this APD would basically you will obtain by collecting the terms which multiply phi I plus 1, and AWI would be the terms or the coefficient which multiplies after gathering the appropriate terms which multiply phi I minus 1, and similarly AED, that would represent the terms which form the coefficient of phi I plus 1. Okay. Next, let us move on to convective term, and the convective term we have many choices available. We can use series scheme for an advective term, and I would just like to make a simple statement or generic statement that it can lead to what we call spurious oscillations, that even though our solution might be a smooth function, we would find lots of oscillations if the so called self-Becquerel number is greater than 2. And to ameliorate this situation, what we normally do is we use Upwind schemes for advective term, and there are various choices available. We will see one of them today, that is first order Upwind scheme. This term, it eliminates the oscillations altogether, but it introduces what we call a diffusive term in the equation, which gives us a highly damped profile. So that is why people say that this particular scheme is highly diffusive. What we mean by Upwind scheme? Let us have a brief look at first the CDS and then the Upwind scheme. So, discretization of advective term. There are various options. Option 1, what we did for this diffusive term, we had used second order accurate CDS scheme. So, shall we use the same scheme for our convective term as well? So, if you use the central difference approximation, so then what we would get? The term which we were looking was d by dx of rho u phi at node I. Since we are looking at node I, in the central difference approximation, the terms involved would be at node I plus 1 and I minus 1. So, this can be approximated as rho u phi at I plus 1 minus rho u phi at I minus 1 divided by the spacing between these 2 points, that is x of I plus 1 minus x I minus 1. So, what is the contribution which we get for the convective term? At APC, in this case what would be our contribution to the ith node term? APC is equal to 0, because on the right hand side of this equation there is no term which contains phi I. And how about I minus 1 of phi I minus 1 of terms coefficient? That is what we said, that is equivalent, that will give us the contribution to the AW term. What will that be? It will definitely be non-zero. Okay. So, can you rearrange and find the out? This I would again leave as a very simple exercise. So, find out what will be the contributions to this APC and AWC and AEC if you use central difference approximation. Now, the remark which we had earlier made was, note, though this CDS is second order accurate, that is accuracy is second order, but it can produce oscillatory results. If local, or we also use sometimes the term cell, local Peclet number. How do we define this local Peclet number? Use the symbol PE. This is defined as rho u delta x by gamma. So, this is the definition of local Peckel number. If this is greater than 2, we are in trouble when we use our series scheme. So, what is the solution then? So, to get rid of oscillations, rid of spurious numerical oscillations, I want to reinforce the term here spurious or numerical, because such oscillations are not actually the part of our exact solution of the problem. They come here simply because of our choice of the numerical approximation or finite difference approximation. We have to use what we call upwind difference schemes. Now, here we have used term upwind. What do we mean by upwind? Upwind comes from normal connotation of when we say the wind is blowing. So, this is an advection-diffusion problem, and the advection depends on the velocity. So, suppose just focus on a specific point in space, it could be a grid point I. Look at the velocity here. Now, there are two possibilities. So, x direction, that u could be greater than 0 or less than 0. So, u greater than 0 would mean what? That is our velocity, that flow is going from left to right. So, what would be our upwind direction? Upwind means that we go against the wind or against the flow velocity. So, upwind direction would be towards negative x direction. So, this is one case. So, now in this case upwind difference schemes would involve what? This would involve values at the nodes which are not towards the right, but instead they are towards the upwind or upstream side. So, some people also use in place of upwind, they also use this term very often, upstream. Okay. Both are synonymously used. So, in this case, so if u is greater than 0, that is flow is in positive x direction, upwind differencing should involve values at upstream nodes. That is, which are the upstream nodes? In fact, they will also involve the values at node I. That is I minus 1, I minus 2, and so on, along with values at node I. So, these are the nodes which we will have in this case, which should be involved in our formulation, and the physical logic given is that yes, the effect of the velocity would be felt more because upstream whatever happens at the upstream nodes, that affects the things happening at node I. So, now our derivative approximations would involve the values at these nodes which are towards the left hand side in this case. Now there could be another possibility. The second case would be that u is less than 0, that is flow is directed in negative x direction. So now in this case, which ones will be our upwind nodes? This is the direction of the flow at a given node location I. So upstream nodes would be nodes I plus 1, I plus 2, I plus 3 and so on. So now in this case our upstream nodes are upstream or upwind nodes are I plus 1, I plus 2, I plus 3 and so on. So use their values, function values at these nodes in finite difference approximation. Now what are the choices which are available to us in the case of upwind difference schemes? The simplest choice is use of a single upstream node. That is our first order upwind schemes, which would essentially correspond to our first order finite, what we call forward difference or backward difference schemes. So here basically we will approximate that d by dx at rho u phi, this would be approximated as what? If our u is greater than 0, then we will have to take the values to the left of I, that is we will have to go for backward differencing. So we will have rho u phi at I minus rho u phi at I minus 1 divided by xi minus x of I minus 1. And if u were less than 0, that is our flow is directed from right to left. So in that case we have to consider our upwind node becomes I plus 1th node. So we will have the values rho u phi at I plus 1 minus rho u phi at I divided by x of I plus 1 minus xi. Okay. So in the first case we have used what we would call a backward difference approximation, and when u is less than 0 we would have used what is exactly our forward difference scheme. Now what are the nice properties of this scheme? No oscillations. So this advantageous feature. No oscillations in numerical solution. For any value of P, that is, it does not matter how small or how large a Becquerel number, that is how strong is the convective term. Our first order Upwind scheme would always give us a smooth solution, and downside is the disadvantage which we should be aware, that is excessive numerical diffusion, or some people also prefer to call it a damping, though it is very difficult to say why this particular term damping is used in this case. And just to give you a graphical illustration, suppose we are dealing with the advection-diffusion of a sharp front. So phi, along this we have got x. The sharp front, suppose it has got a constant value up to certain point, then suddenly takes a jump and the values go to 0. Now, if you use so this is our so called exact solution. If you use a CDS based scheme, it could give us this sort of a solution, lots of oscillation. But if we use this upwind difference scheme, we might have a fairly smoothed out solution. So, you can easily say that this is as if we have introduced additional amount of diffusivity in our system. Okay, now is there any way in which we can improve the situation? Yes. One of the improvements which you can immediately think of is use a higher order upwind scheme. So, improvements, higher order upwind schemes. For example, a second order accurate FDS or BDS, that is forward difference or backward difference scheme. But surprisingly, this is also prone to oscillations. Okay, so this is not a real improvement. Then our next thing is to go for what was developed recently, which are called high resolution TVD schemes. So, these work similar to our upwind scheme, but we are not going to discuss these in detail at the moment. I would in fact leave it as reading assignment to you. Okay, that is what is our summary, that first order upwind scheme, it works beautifully in damping out or in eliminating the spurious oscillations, but it is highly diffusive. Second order upwind scheme based on one sided FDS or BDS, it again prone to oscillatory behavior. So, in our usual or commercial CFD codes, we go for what we call total variation diminishing or TVD schemes. This one possibility, and another set of schemes are called essentially non-oscillatory schemes. And our first order upwind scheme in fact is a member of these generic TVD schemes. So, for details I would suggest that you refer to the books by Chung and Versteeg and Malalasekara on computational fluid dynamics. I will give the full reference of these books towards the end of the lecture. Now, let us move on to our computer implementation aspects. So, if you want to develop a CFD code, these are the aspects which we must consider. That is to say, first, which algorithms we are going to choose to solve our partial differential equation governing a specific CFD problem. Now, we have primarily these three popular choices: finite difference method, finite volume method, or finite element. We had already discussed in this module in detail finite difference method. So, in the next lecture we will discuss development of a simple one-dimensional code based on finite difference. So, in set of algorithms, first choice is our discretization method, and the next is the solvers for discrete systems. So, we have to make these choices. In fact, in a useful CFD code we have got to provide for a set of solvers for the discrete systems. Then which language to choose and which paradigm, programming paradigm. The most popular languages in CFD applications have been Fortran, and Fortran has been used since beginning, since 1960s, and more recently C and C++ have been claiming the space which was earlier exclusively occupied by Fortran. Then should we go for procedural approach, which is the way the Fortran works, or should we go for object oriented code, which gives us what we call an easily modifiable program. So, we have to make a choice of these two. And then the last term thing which we have to think of is the choice of the data structures. Should we go for fixed size arrays, or should we go for the simple records arrays, or we go for what we call some more complicated classes, structures, or records. Class and struct, they are part of a C language. Records are now available as a feature in modern Fortran language. So, should we go for these ones, bit more complicated ones, or we go for simple arrays. The next one is, should we go for the fixed size arrays. That is to say, we have, when we are writing the program, we would think of a size, a maximum number of nodes which one might use in discretization, make all arrays of that size, or we can allow the arrays to grow. That is, for different problems, different users might choose different grid sizes, and then the grid size can be input, and based on the grid size, the sizes of these arrays or the structures or records could be considered. Now, as far as the algorithms are concerned, with which whether you are going to choose finite difference, finite volume, or finite element, we will discuss finite volume and finite element in bit more detail in later modules. It would depend on your preference. Majority of the commercial codes are in CFD are based on either finite difference or finite volume method. There are few codes available on FDM as well, but it's your call. If you are developing your own code, which one you are more comfortable with. Okay, and this is for the common practice today, that FDM and FVM, finite difference and finite volume method, they are more popular in commercial CFD applications, and finite element is preferred in structural analysis. There is no reason why one cannot go for FEM for writing as CFD code. Now, next is solvers for discrete algebraic systems. In our usual code, we should provide a set of iterative solvers, and of course these iterative solvers require what we call preconditioners. Now, these two aspects we will consider in our next module on solution of algebraic equations. Now, I have not mentioned any direct solver, because in our usual CFD, when the grid size is pretty large, number of nodes are very large, we would rarely if ever use a direct solver. Similarly, if you have got a time dependent problem, we have to use what we have to provide for a set of one step and multi step time integration methods, both of implicit type and explicit type, so that depending on the problem, the user can opt for either implicit one or an explicit approach. Now, I would just like to point out here that as it regards the choice of the language, you can choose either C, C++ or Fortran, but please remember, if you want to become a CFD developer, a basic knowledge of both of these languages is required. The reason is very simple. Fortran has been used, in fact Fortran language was developed exclusively for scientific programming, and so lots and lots of work is available in Fortran. There are many libraries which are available in Fortran. Majority of the codes which are available in commercial and free domain, they are based on Fortran, and if you want to make use of those libraries, the user must know at least must have a working knowledge of Fortran and a good knowledge of C or C++. Now, regarding procedural object oriented programming, I would like to make one small comment that object oriented code is what we call, it provides for better software engineering in the sense that the codes are easily modifiable, easily extensible, because you will work in terms of classes. New classes could be derived based on those classes without affecting the current implementation. So that is why it is called a better software engineering, but this object orientation has got severe performance overheads, and CFD applications are what we call highly compute intensive. So we would like to minimize these non-essential overheads to the extent possible. Hence, in CFD programming, our preferred programming paradigm is procedural programming. We would not use, in fact majority of the software developers in CFD, they do not use object oriented code. Procedural programming is preferred. Now, few more guidelines, or what I would say the basic guidelines for software development. Whichever language you choose, whether you choose Fortran or C and C++, there are few basic thumb rules which you should follow. So, basic guidelines for development of CFD code. In fact, these guidelines apply, they are taken from software engineering, so they apply for development of any computer code, and they are equally pertinent to our CFD applications. So the first approach which we should use is what we call design your code as what we call modular. That is to say, the CFD code consists of a set of modules which can be independently developed and tested before combining together. This is very similar to a normal engineering practice. For instance, if we want to develop or we want to design a car or manufacture a car, what do? The entire car is not manufactured at one go. Different subsystems are designed separately, they are manufactured separately. test it separately, and once each component has been tested, then it is assembled together to get our final product, that is our car. Similarly, if you want to develop a nice CFD code, we should break our big code into small modules or pieces, develop each module separately, test it, and only then combine it together. And second guideline which you should follow is document your code. Now, by documentation, there should be two set of documentations. Two set of documents. The first one is your design document, that is description of which will contain your description of algorithms and pseudocode. Okay, in hard copy form. And the second, and which is equally important, is provide liberal comments. Comments are set of statements or set of lines in a code which are there only for a human programmer, they are ignored by the compilers. So, we have to provide liberal comments in our code, that is specifically for each routine or function. In Fortran we use the terms routine or subroutine, in C or C++ we call them as functions. For each subroutine or functions, one should provide number first what that function does, objective of the function, the second description of input and output parameters, and you should also put a date stamp. Okay. Date stamp which would help you to keep track of when that particular routine was written or modified. Okay, so this is the first guideline, that you should develop your code as a modular code. And the second aspect which we had was a documentation. The third aspect, third aspect which is equally important is incremental development and testing. Incremental development and testing. So, there are two ways. You are very ambitious, you know the knowledge of your domain, you thoroughly know a computer programming language, you also know your CFD algorithms, and so you might be tempted to go for write a big piece of code, okay, and then try and run it. It might in all probability 99% chances would be that your code would fail and you would find it very difficult to detect where you had made an error. So what we should do is we should take an incremental, a step-by-step approach, and it's incremental, which we can also call a step-by-step. That is, we add one routine at a time, add one routine or function at a time. Okay. Test this function. Test this function for a most possible or most likely values of parameters to verify that whatever algorithm has been coded in that function that works correctly, and secondly for extreme values. The parameters to detect which are the likely situations in which our algorithm might fail and what sort of error statements or exit cases we need to incorporate in our code. So if you follow this incremental approach, you can, starting from a code of let us say 10 lines, you can easily build it step by step into a code which might run into millions or billions of lines. So even your very big commercial code which might contain millions of lines, that has been built up using this incremental development and testing approach. There might have been many programmers who were involved in development, but each programmer was assigned a task of developing a set of routines, a set of functions or set of modules, and in developing their modules or functions they had followed or they are instructed in this industry to follow this incremental development and testing approach. The code has to be written in a structured format, it must be documented properly both in a hard copy form as well as inside the code, and then this unit testing, it ensures that our code has been debugged properly and it is ready for what we call final integration. So once we have unit tested thoroughly, the task of integration would become a lot easier and we will get a reasonably error free code. We cannot say that it is a code which we have developed or a product which we have got that is perfect, that is 100% error free, that can never happen in a human endeavor, but by following this incremental approach we can minimize the occurrence of those errors. So we can confidently say that we have developed a reasonably error free code. We are going to follow these guidelines and in developing a very simple one dimensional heat conduction code based on finite difference method. That is what we are going to discuss in the next lecture. We will primarily focus on our approach so that you can use the same approach to develop bigger codes for let us say multi-dimensional problems. Okay, the references which we have referred today specifically for some algorithms, there are two which you can refer to: Computational Fluid Dynamics 2nd edition, Cambridge University Press by Chung TJ, which is published in 2010. Similarly, you can also refer to Furtziger and Parik's book published in 2003, Computational Method of Fluid Dynamics, In the next lecture, towards the end, I will give you a consolidated set of the books or references which would be very useful for learning finite difference method and the CFD application based on that.